Welcome back to this short series on the fundamentals of control engineering. Today we introduce integral transforms, and in particular the Laplace and Fourier transforms. But to start with, let us first review the Fourier series. So you might have seen from some previous class that for any periodic signal, we can obtain our representation in terms of a Fourier series. So a periodic signal is a signal such that it repeats itself after some fixed period of time, and its Fourier series is a representation which takes the form of a sum of sine and cosine functions. The term 2 pi over t is sometimes denoted as omega, which is a frequency expressed in radians per second. And here, to avoid confusion, we just give it a not index to denote that the fact that this is a fixed frequency. Now, Fourier series have different representations, and in particular, we are interested here in the called exponential representation of the Fourier series. So let us quickly derive it. And here we make use of Euler's formula to transform the sine and cosine functions into complex exponentials. And now we can collect the plus and minus I, k, omega naught t terms. And we introduce the coefficients ck and c minus k. Note that these coefficients will be in general complex, as they also contain the 1 over 2i coefficient here, currently from ak and bk. Now we can put everything together by just letting the sum run from minus infinity to plus infinity. And what we obtain is the following. And in general, we could look at the coefficient ck as a function of the specific frequency omega equals k omega naught. So we could denote them as ck equals capital X of k omega naught. And this will come handy in a minute. Now, as an example of this, you might have seen the representation of a square wave as a sum of sinusoids. And sometimes this is also represented as the coefficients of the sinusoids. So in particular, here we only have odd functions because the square wave is odd, and the coefficients will be something like this. So they will be at odd multiples of omega naught and will typically be decaying in amplitude. And in this case, we are referring to the coefficients of the sine expansion of the square wave. So we only have positive values of k. And to find such coefficients in the expression we just derived, the one with the exponentials, we can use the following expression. Now, this expression here can be extended to the case of non-periodic signals to obtain what is called the Fourier transform. Now, the expression we have just seen can be extended to the case of non-periodic signals to obtain what is called as the Fourier transform. So the Fourier transform of a signal x, which will be our x, and this time it will be a function of continuous frequencies, not just of discrete samples in the frequency domain, will be exactly what we have seen. So it will be the integral of the signal x of t multiplied times the Fourier kernel e to the minus I omega t in the t. And since we don't really have a period in this case for a non-periodic signal, then this integral will be evaluated over the interval minus infinity to plus infinity. While to find an expression of the signal x of t in terms of this Fourier transform, we will need to move from a discrete sum to a continuous integral. So x of t will be the integral from minus infinity to plus infinity of our coefficients x of omega, or actually our Fourier transform x of omega, times e to the I omega t. in the omega. So this is an integral, so we need to add the integration variable. And when this integral is computed, the omega variables is eliminated and you are left with a function of time. Now, a note about this transform is that it works for, let's say, well-behaved functions, where this typically means that the function we are considering must go to 0 for minus infinity and plus infinity for this integral to make sense. So we'll have some function that goes to 0 on both sides. We can extend this expression to periodic signals by using a bit of a stretch. For example, you might have seen the transform of a square window, which satisfies our property, which is given by this function here. So signals that satisfy this property are called sometimes energy signals. And for this class of signals, the Fourier transform is well defined. We can extend the Fourier transform to periodic signals by making use of the so-called distribution theory. So for example, let us consider the case where x of t is the cosine of omega naught times t. And this can be expressed as the integral of x function of omega times e to the minus I omega t in d omega. This is also called Fourier's inverse transform. And again, making use of Euler's formula, we can write this as integral from minus infinity to plus infinity of x of omega times the sum of the cosine of omega t plus I times the sine of omega t in d omega. And to solve this problem, we can make use of the so-called Dirac's delta function. This is actually a distribution, and it has the following property. The function delta of x minus x naught, if we apply it into an integral to a generic function of x, f of x, returns the value of f in x naught. This is called the sampling property. And so we immediately find that the solution to this problem is given by x omega equals 1/2 of delta of omega minus omega naught plus delta of omega plus omega naught. And you can verify by yourself that this choice of x omega returns the original signal when plugged back into the integral we have just written. And we can represent this in terms of the Fourier transform as two Dirac's impulses into the frequencies omega naught and minus omega naught. And typically note that x of omega is a complex function, so this would be the representation of the magnitude of x. So now we're ready to move on to the Laplace transform. What the Laplace transform is a generalized version of the Fourier transform. And to motivate the need for such an operator, we start by observing that we have seen that for LTI systems, the solution x of t will in general be a superposition of some exponentials of the form x e to the a, let's say kt, times e to the plus or minus I omega k t. And so we will have combinations of exponentials with different decaying rates or growing rates given by ak and different frequencies for the oscillating part. Now, if the frequency might be 0, which means that we have a purely exponential term, or the decaying term might be 0, which means that we have a purely oscillating term. Now, this part could be Fourier transformed by a bit of a stretch using distribution theory. But the term here might be a bit of a trouble because this doesn't really behave as well as we require for the Fourier transform to work. And in particular, we see it immediately if ak is a positive, a growing exponential. The function will definitely not go to 0 for t that goes to infinity. So we can't Fourier transform this term. So one possibility would be to multiply x times some regularizing function, which helps us deal with this term. As an example, let us assume that x is just given by an exponential e to the at times the cosine of some frequency omega naught times t. And if a, for example, is a positive variable, then we'll have a growing exponential. Now, let's say we wanted to Fourier transform this signal. And let us consider the integral from minus infinity to plus infinity of e to some minus sigma times t times x of t. And then we take the Fourier transform of this. So we multiply it times e to the minus I omega t and integrate over t. Now we can take these two terms and collect them into a single complex exponential. So e to the minus s t. And so we call this x of s, where s is a complex variable. And this, by definition, is the Laplace transform. Now we immediately notice that if sigma is equal to a, we are left with the Fourier transform of a cosine, which we have just seen. And we know how to solve this Fourier transform. So let us draw a representation of what we have found. Let us consider the plane where we have sigma on one coordinate and omega on the other one. Now, choosing sigma equal to a means basically looking at one specific line on this plane. So if this is a, we are looking at this line here. And on this line, we know that the Fourier transform of the signal we have just seen is just two Dirac deltas at minus omega naught and plus omega naught. And of course, the Laplace transform of x will be a complex function. So for now, we'll just plot its magnitude. So let's say this is the modulus of L of xt. Now, when sigma is larger than a, the decaying term e to the minus sigma t will be stronger than the exponential term e to the at. So our integral will converge because our function will actually converge to 0 for t that goes to infinity. So we'll have typically for any sigma which is larger than a some well-behaved function. While if sigma is smaller than a instead, the growing exponential e to the at will actually win in this case, and our integral won't converge. So there's unfortunately no Laplace transform here in this region. We can define a as the so-called abscissa of convergence of the Laplace transform. And this is the minimum value of sigma for which the Laplace transform makes sense. So what we have is that our Laplace transform generalizes the Fourier transform for a more general class of signals. And in particular, we have that it is well defined for sigma larger than some minimum value, as we've just seen. Moreover, if this minimum value is smaller than 0, the Fourier transform is just a special case of the Laplace transform. And in particular, it is just the Laplace transform evaluated at s equals I omega. And finally, we are usually interested in the points where the Laplace transform is either 0 or infinite. And in this sense, we can use a, let's say, synthetic representation of the Laplace transform, which looks like this. We can take the Gauss plane and just draw some axes where the poles are, so where the points where the Laplace transform goes to infinity are. In this case, they are just a complex conjugate pair at my A. And in general, we might also have some zeros for the Laplace transform, and they will be denoted by small circles on the Gauss plane. So the Laplace transform has some interesting properties, and in the next video we will see how it can be applied to linear dynamical systems.